Okay, so good morning, everyone. Now we are recording. So let's just get started. Um, okay, let's see. Okay, so we are continuing from where we left off, right? So we were talking about faces of a plane graph and the boundary of a face, and in particular, we also define the degree of a face, which is the number of edges in its boundary, where you count the cut edges twice, right? And by doing so, you get something which is similar to the handshaking lemma. We'll call it the dual handshaking lemma for reasons that will become clear quite soon. And what it says is that if you sum up the degrees of all the faces in a graph, then you get 2 times the number of edges because every edge is counted twice. Either the edge belongs to two distinct faces or it is a cut edge and it is counted twice for the same face, right? Good. All right. Another, I want to introduce one notation. I forgot to mention this earlier. So the boundary of a face, you can regard it either as a subgraph, right? Or you can also regard it as a set of edges. And when we do that, we will use a notation, may be regarded as a set of edges. And then the notation for that, which again will become clear very soon, is partial of f, where f is the face. So let's take one quick example. In our graph here, the partial of f5, for instance, it is all the edges that are in the boundary of f5. So that would be e4, e5, e9, and e10. Okay, good. All right, so far so good. I just want to state some quick facts which will be just observing and not proving. Well, one of them follows from the Jordan curve theorem, which also we did not prove. So one of them is the following, that the planar embedding of a cycle has exactly two faces. Okay, so right, so this just follows from JCT. What about trees? Anyone? How many faces does the planar embedding of a tree have?
Only one.
Exactly. Right. So for any tree, you observe that there's exactly one face, right? So planar embedding, you can also prove this by induction because any statement on trees can generally be proved by induction using the leaves. Planar embedding, well, most statements of a tree has just one face. In fact, it reminds me of of an interesting thing that Robin Thomas told us during the lectures, is that if you ever come across a statement about trees that you cannot prove by induction using the leaves, you know that it is a fairly non-trivial statement. And another thing I want to mention is that the face boundary in any connected plane graph for any face is also connected. This is not true for disconnected graphs. For example, here you can see clearly that the face boundary of this face is a disconnected graph. But for a connected graph, it will always be connected. Okay, so each face boundary of a connected plane graph is itself connected. Okay, So hopefully those statements are believable. We can accept them without proof. All right, so let's move on. Okay, let's talk a bit more about the boundaries of a face and then prove a nice result. So let's go to this drawing here. Now you see, you can think of, in fact, we will also state this without a rigorous proof. If you take any face in a plane graph, a connected plane graph, then the boundary, you can think of it as a closed walk. So let's consider this face F5 that we have redrawn here. So what you can do is, you can, okay, so I'll just do it in the original drawing. So for F5, you can see that you can start walking on this point, and you go along the entire face, and gradually you come back to where you started from, right? And so in graph theory terms, what you have here is a closed walk, right? Notice that in this case it is not a cycle because you are repeating the cut edge twice, right? So it's not a cycle. However, I believe that in this particular plane graph, all the others are actually cycles. All the other boundaries, if you think of them as closed walks, no, actually, even F1 is an exception. I'm sorry. F1 is also an exception because you would start walking here, and then you would go around like this. So far, so good. This looks like a cycle, but at this point, you go around the loop, and now this is no longer a cycle. It is a disjoint union of two cycles in this case, right? So when is it a cycle? Any guesses? Are there graphs for which you think that the boundary, the closed walk of the boundary, would actually be a cycle?
Simple graphs?
Simple graphs. Okay, so that's a good guess. So you've gotten rid of loops. There is still one issue. What about these cut edges? Right? You may still have a cut edge. So even if you remove the loop E7, you still have a face here whose boundary is not a cycle. It is a closed walk, but it is not a cycle. Right? So
Two
you also
connected
cannot,
simple.
okay, two connected. Right. So two connected simple graphs turns out to be a correct class of graphs. Right. So you cannot, so as you observed that not only is cut edges are a problem, cut vertices are also a problem. A cut vertex is something similar to the vertex V1 here. Instead of a loop, you will have something, some other graph attached there, right? So two connected. In fact, we will prove it that for any non-separable graph, this is true. Right? So it's basically two connected graphs. Okay. So let's go there. All right. So in a connected graph, the boundary of each face is a closed, may be regarded as a closed walk because we are basically looking at a different viewpoint. Right. And in particular, the cut edges will be traversed twice. Cut edges are traversed twice. Okay, good. All right, so I'll not show an example because I already drew one, right? So let's prove the following. I won't write down a rigorous proof. I'll just discuss the intuition behind it. So Whitney in 1932 observed the following. In a non-separable plane graph, except K1 and K2, so then you're basically left with two connected graphs. The only other graph is K1 with a loop on it. Each face is bounded by a cycle. Okay? Good. Before we prove this, which I said we won't write down a rigorous proof, we will just discuss the main idea behind it, and I will leave the writing details to you. Before we go there, I want to state a cool consequence of this. Let's take a graph which is two connected. Something like this. Okay, so we've got a two connected or non-separable plane graph. You see that each face is bounded by a cycle. There is a cool consequence of this. I'll give you a hint. It has something to do with cycle double covers. Do you see it? I claim that this graph or any non-separable plane graph has a cycle double cover without cut edges. Well, non-separable implies no cut edges. I just need to throw out K1 and K2. Right. Okay, so so you look at all the faces and you look at their boundaries. Right, so this is one face. So you get one cycle here. You get another cycle, yet one more, and this one here. And that is a cycle double cover. Right, so you just look at all the faces and you take their boundaries. They are all cycles. Every edge will be counted exactly twice because it appears in two faces. So it will appear in two cycles, right? Because we don't have cut edges, right? And that's it. That is what we want in a cycle double cover. So the cool thing about cycle double covers is that it's clearly true for planar graphs, right? But the conjecture is saying that it's actually true for all graphs. Right? So the cycle double cover conjecture holds for planar graphs. Okay. So now, how would we prove this statement? Anyone? How would you prove that in a non-separable plane graph, every face is bounded by a cycle? What are the tools that we have for non-separable graphs?
Year decomposition, maybe?
Exactly. Let's go with the decompositions. So in the same spirit as Robin told us about trees, most statements that are specifically stated for non-separable graphs, if you can't prove them using ear decompositions, they are probably quite hard, right? So one example, of course, is a cycle double cover conjecture. No one knows how to prove it using ear decompositions, and it's open. So yeah, so let's use ear decompositions, right? So okay, so what does ear decomposition theorem tell us? That we can always build the non-separable plane graph G by starting from a cycle, and at each step we add an ear. Okay, so let's start with the cycle. That's the base case of our induction. So clearly for a cycle, there are two faces, both of them bounded by the cycle itself. Okay, so we are using ear decompositions. So if your graph is G, then you get the ear decomposition G0, G1, G2 up to GR, where G0 is a cycle. So the statement is true for G0, holds for G0, right? Now let's suppose that the statement holds for some GI where I is at least 0. So suppose holds for GI. So how am I getting the graph GI plus 1 from GI? I am adding one ear. So in GI, I know that every face is bounded by a cycle, right? So I'm going to look at so rather than looking at these as abstract graphs, I'm going to view them as plane graphs, right? So I'm going to look at their planar embeddings. So I have the graph GI and its planar embedding, and I'm going to add an ear to this to obtain the next graph GI plus 1. Well, if I add an ear, right, so I'm joining 2 points by an arc in the topological sense, then the 2 points have to be on a common face, right? They cannot not be on a common face, otherwise I would not be able to connect them by an arc, right, by the definition of a face. So they belong to a common face. So let's say I'm adding the ear pi. So let's say GI plus 1 is GI plus pi. I don't know what okay, this is fine. So let's say I'm adding the ear pi, okay, and pi has ends uv. So then my claim is that u and v belong to a common face in GI, in the planar embedding of GI, right? So there is a face in the graph GI, and u and v both belong to that face, right? Now this face, by the induction hypothesis, is bounded by a cycle. And what we are doing is we are adding an ear joining these two vertices. So that's a path, right? Okay, so which means that we are drawing that path in that face. All other faces, they are unaffected. Their boundaries will remain the same. In particular, they will remain cycles. The only face that is affected is the face in which you draw the ear. So that face is no longer a face in GI plus 1. It splits into two faces, F1 and F2. Or if we are using small notation, it splits into F1 and F2, right? And now observe that the paths joining U and V, one path joining U and V on the original face, along with the ear, bounds one of these faces, and likewise for the other face. So both of the faces that you have created by adding this ear, they are again bounded by cycles, right? And that completes the proof. Does everybody agree? It's fairly straightforward. It's very intuitive. Okay, so that's just another application of ear decompositions. So in non-separable plane graphs, generally when you think of a plane graph, you tend to imagine non-separable ones, and you tend to think that all faces are bounded by a cycle. So that's for a reason, which is this theorem. right? Good. I want to state another corollary that will be useful to us later when we try to prove Krotowski's theorem. So, okay. So as I told you, in the proof of Krotowski's theorem, we are first going to reduce the problem to three connected graphs. Okay. And then we are going to prove the statement for three connected graphs. And that will prove it for all graphs by our first step. Okay. So, okay. So that's the reason this corollary is going to play an important role there. Yeah. Okay. So let me just state it and then I'll explain why it's true. In a loopless three connected graph, the neighbors of any vertex lie on a common cycle. Let's just take a quick example. Okay. So supposing I take this simple three connected plane graph. Okay, notice that the statement is not about plane graphs, it is about abstract graphs, right? But in order to prove it, we will consider an embedding and we will use the previous result and we'll get a cycle, and that is how we'll prove it, right? So take any vertex here and now look at its neighbors. Okay, they lie on a cycle. The idea to prove this is basically erase this stuff here. Okay, so I should have drawn it differently. Okay, let me draw it again so that I get what I want. Okay, let me put this vertex at the end. Okay, now let's look at this vertex again. Okay, so its neighbors are these three. So to prove the statement, the idea is to erase this vertex from the planar embedding. Now this vertex was a point in the plane, so we'll keep that point in mind. So now what we have, because we deleted a vertex from a three connected graph, which was loopless, what we will get is a two connected graph. Right? It will be a loopless two connected graph, which is basically the same as a non-separable graph. If you have a good minimum number of vertices, blah, 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 right? So what you have here is a non-separable graph. You have its planar embedding, and you look at the point that corresponded to the vertex you deleted. Well, the only way you would be able to connect that vertex to all of its neighbors is if all the neighbors were on the face boundary uh, for the face in which this vertex, the point is located, right? So we are looking at the graph G minus V, but we have this point corresponding to the vertex V. It is located in some face of G minus V. So when you introduce the vertex V back into the picture, and you're able to connect it to all of its neighbors by drawing edges, that is because all of the neighbors belong to the face, belong to the boundary of the face that contains this point V, right? And so now you take that face boundary and it is a boundary that contains all the neighbors of the vertex V. This is actually the proof of the statement. So I won't even write it down. It's some 3-4 lines, but it's basically what I explained. Does it make sense? Is the proof clear?
Yes, sir.
Good. All right. So that's it. Right. So consider, I'll just write maybe a sentence. Consider a planar embedding of G and delete V and use previous result. Okay, good. So as I said, we will use this when we get to proving Krotowski's theorem. Okay, so now I want to move on to planar duality. All right. So I will start by an example, maybe the same example I drew a few minutes ago. Okay, so let's say we have got this graph. Okay, we have got this plane graph. G, yeah, G is a plane graph. We will construct another plane graph from this graph. So I will show you by example that when you draw it this way, you get another planar graph because we'll actually get a planar embedding of the new graph. But the definition is going to be independent of how you draw the new graph. It's going to be defining an abstract graph, but when you go through the process of drawing it, it becomes clear why that new abstract graph is also planar. It might be a proof on your assignments, I'm not sure yet, but it's not something we'll be proving in the lectures. So let me show you how we draw this new graph. Some of you may have already seen this in your previous courses. So the idea is inside each face of this graph, put a vertex. So we have got 4 faces. And now, whenever 2 faces share an edge, you connect them, you connect those corresponding vertices in the following way, right? So here you have a face F1 and F2. They share the edge that you see. So I'm going to join these two. Right? And I'm going to do this for every time 2 faces share an edge, right? Which basically means that for each edge, I'm going to draw a corresponding red colored edge for my new graph. Okay, so have I completed it? Well, check whether for each black edge, you see a red edge that crosses it. Yes, I see one. So this is the dual. This red colored graph is your dual graph. Okay. Notice that it becomes more interesting when you have cut edges and loops. So since we are allowing them, let me take an example where we have cut edges and loops. Let's just make a simple example, not too complex. Let's do something like this. Okay. So what happens in this case? Well, let's use red color for the dual. So I've got a vertex here, I've got a vertex here, and I've got a vertex here. I join these two, I join these two, I join these two. What else? This, if you look at this loop, it is the boundary of 2 faces, right? So these are the 2 faces. So we have drawn one edge for each black edge, except for the cut edge, which I left for the end. So the cut edge, by convention, it it is sharing the bound. It is being shared by the same face twice, right? You're counting a cut edge for the same face twice. So what we'll do in the case of a cut edge is this, right? Another way to think of it is for each edge, draw a small segment crossing it, and now on this side, which face do you belong to? Well, you go to that face. On this side, which face do you belong to? You go to that face. Okay. So notice that the loop has actually become a cut edge in the new graph, and the cut edge has become a loop in the new graph. A cut edge is a bond, and a loop is a cycle. There is a reason behind this, right? So you see where we are going. You're going to see some connections between bond spaces and cycle spaces through the lens of duality. Okay, good. So is it clear how we are constructing the plane graph? I'll put down the formal definition now, but I thought it was better to start with an example. Okay, so then let's write down the definition. And as I said, the definition is not going to define a plane graph. It is actually going to define an abstract graph. But when you draw it in this way, it becomes clear that it is a planar graph, because you immediately get a planar embedding from the original planar embedding of G. Okay, so given a plane graph G, one can define a second graph G star as follows. I'll make it clear here that this is abstract, not a plane graph as per definition. It just happens to be planar, and so it has plane embeddings. So the idea is for each face f in G, okay, for each face, there is a vertex f star in the dual graph. Okay, and likewise, for each edge in G, there exists an edge E star in G star. Okay, and okay, I didn't put this definition, so maybe I'll just. So remember that an edge is incident with two faces, and if it is a cut edge, then it is incident with the same face twice. So what we will say is that the two faces are separated by the edge. Okay, so I'll just write it down here. In G star, we will make the vertices F star and G star adjacent by the edge E star. So what I mean by this is that the edge E star joins F star and G star. Okay, if and only if the corresponding faces F and G are separated by the edge E in the graph G. Okay, so what I mean by this is that E lies on the boundary of F and G. Okay, geometrically it makes sense to call them separated because it looks something like this, right? You have there is a vertex here, and so what you will get is a loop. If this is your vertex corresponding to the face, you will get a loop. Then f is,
Sir, your
yeah, go
voice
ahead.
died for a few minutes.
Oh, I see.
Like
Okay.
I don't think we could hear for maybe like in G star F star is adjacent to G E star.
Okay. Okay. So should I go back to defining the adjacency relation?
In G star, yeah, in G star
Right.
F star is adjacent to, yeah.
Right.
From there
So
I could
in
hear it.
right. So okay. So let me do that again, and let's see what happened here. Okay. Now audible, right?
Yes.
Yes.
Okay. Okay. Good. So what we have done is for each face we have put a vertex in the dual graph, and for each edge of the original graph we have an edge in the dual graph. We are denoting elements of the dual by star, right? So we have vertices f star and edges e star, and two vertices in the dual, they are joined by the edge e star. So the vertices f star and g star are joined by the edge e star if and only if the faces f and g are separated by the edge e in the graph G, right? And what I mean by the two faces being separated is that the edge e lies on their boundary. So you can imagine it looks something like this. E lies on the boundary of two faces, and so we are going to say that the two faces are separated by the edge E. Okay, and let's make some quick observations. If the edge is a cut edge, then F is equal to G, and so what you get is a loop. So this implies that the corresponding dual edge is a loop. And the converse is also true, that if the edge is a loop, then the dual edge will become a cut edge. So that is actually a bit interesting. So if E is a loop, then E star is a cut edge of G star. Do I want to explain this? I don't. I want you to think about it. Okay? So make some more complex examples and try to see why a loop becomes a cut edge. And it will actually follow from some more general things we'll prove as we go further. But it might already be a good idea to get started to think about it. Okay? All right. So is the definition of the dual clear? Okay. So if there are no questions regarding this, let's make some more observations. Um, so I want to explain why we use the notation partial for the boundary, y partial for the boundary of a face. Okay. All right. So let's go to an example. Okay. So let's look at this example here. Um, let's say I don't want to use red color for anything for the original graph. So consider this face here, F, in the graph G. So G is your black colored graph. Okay. And the corresponding vertex is F star in the red colored graph. Okay. So what is the partial of F? partial of f is all those edges that are on the boundary of the face f, right? So let's put them in some color green, let's say. Okay, so on the boundary of f you have these edges. So it's basically the cycle bounding the face because this is a non-separable graph. So these green colored edges, they correspond to partial of f, the boundary of f. Okay, and notice that this is exactly the same as the edges incident at the vertex f star in the dual graph. So for each of the green colored edge, you look at the corresponding edge, and I'm coloring them blue, right? And what you have is basically all the edges incident at this vertex, right? Intuitively, you can see why this is happening. So the partial f, these edges correspond exactly to partial of f star, where f star is the vertex in the dual graph, right? So this is a notation we have used earlier for the edges incident at the vertex, except loops, right? We removed loops because they are not part of a cut. So that is the reason we are using this notation. So that's the next observation I want to state. So if G has no cut edges, then the graph G star has no loops. And in this case, the partial of f star is exactly the following set. You take all the dual edges for the edges that are incident in partial of f, in the boundary of f, right? So this is the cut corresponding to vertex f star, right? Um, and this here is the boundary of the face f, right? So we are overloading the partial notation, but this is the reason we are doing it, right? So it should be clear from the context whether we are referring to a face or a vertex, and you will use the notation partial accordingly. Okay. And another observation is that the dual of a plane graph is another planar graph. So we are not proving this. I tried to illustrate by an example why it intuitively seems true. Although I'm thinking perhaps you might deduce it as a consequence of something on the assignment. Okay, so we might prove it on assignment 3. All right, good. I want to state one more proposition, and this one again, I'm not going to prove it. I just want you to think about it on your own, and the proof is in the text, so you can look it up. So let's take a disconnected graph before I state this, and let's look at its dual. So although this graph is disconnected, if you take the dual, you've got a face here, you've got a face here, and the dual looks like this. right? And this is connected. So it turns out that the dual of any graph, irrespective of whether the original graph is connected or not, is a connected graph, right? And the short proof of that, without going into details, is that the plane is a connected surface. You can go from any point to any other point in the plane, and that is essentially why the dual of any graph is going to be a connected graph, dual of any plane graph. Okay, so I'll put it as do it yourself. All right, good. Um, okay. So yeah, there's a lot of things I want to state, which we are not proving several of those things. They are intuitively clear. We will prove some of them on the assignments. Okay. Uh, Another thing I want to mention, well, clearly at this point you're wondering if the dual of the dual is the original graph, right? And if you look at all these examples, you see that it is the case. If you were to take the red graph and then you were to make the dual of that, you would get exactly the original graph you started with, or at least the same abstract graph. You may have a different drawing, that's a separate matter, but you will get the original graph, right? And that turns out to be true. Again, let's see. So this is an exercise in Bondi Murthy. We might have it on the assignment. I'm not sure. And so if G is a plane graph, then show that the dual of the dual is isomorphic to G. And this is true if and only if, oh, actually, this example, it should fail. So it should fail for this example. Let's see. If I were to draw the dual of this graph, of the red colored graph, let's see what happens. So notice that the red colored graph is this graph. Okay. So here we should fail. The dual should not look like the original graph. Let's see why that happens. So you need the condition that the graph is connected. So let's see. We'll put a vertex here, we'll put a vertex here, and we'll put a vertex here, and a vertex here. Okay. And notice that this is not the same graph as the one I had started here. What I have here is a K3 with an edge. Yeah, so this red colored graph is basically like this. And that's not the same as the black colored graph that I had drawn in the first picture. Okay, so this is true. This is true if and only if the graph is connected. Actually, I will have to prove this myself to put it on the assignment. So I haven't done it yet. So for now, let's just leave it as an observation. So for a connected graph, the dual of the dual is the original graph again. But it is not true for disconnected graphs, as you can see from this example. So you started with a K3 and a K2, but when you took the dual of the dual, you got a K3 and a K2 sharing a vertex. So you lost some structure there, right? It's not exactly the same graph, although it is similar, as you can see. Okay, good. All right. Another thing I want to state is that even if you have the same plane graph drawn in two different ways, you could get two non-isomorphic duals. So I'll leave this as an exercise. Isomorphic plane graphs. So when I say isomorphic plane graphs, I mean that the corresponding abstract graphs are isomorphic, but the two drawings you have, they are not the same. Isomorphic plane graphs may have non-isomorphic duals. And I'll just give you an example and you can draw the duals on your own. So take this graph that we have drawn before. Actually, I need to remove one edge, sorry. And consider the following drawing, where I'm going to flip the triangle outside. Okay, so clearly these two are isomorphic, but they are two different plane graphs. You can observe that the face boundaries are not the same. And if you draw the duals, you will get two different graphs. They will have the same number of vertices, but the way they are connected will be different. In fact, in this particular example, you will actually get the underlying same graph to be the same, but the multiple edges is what makes all the difference in this example. Okay. What we will be proving. So notice that this example, so I'm already at 8:55, so I shouldn't be saying more things anymore. Okay, so we'll start from here tomorrow. Make the duals of these graphs and notice that they are non-isomorphic, and we'll start from here tomorrow. Okay? Right. Good. Any questions or concerns? Anything we discussed today that wasn't very clear? Or that you would like to see a proof of and we did not prove, then I can think about those things. So I am myself quite curious to see how one proves this statement. I haven't proved it recently, at least. So, yeah. Let me know if you have any thoughts on it. But I'm going to try this myself. All right. So if there are no questions or concerns, then feel free to leave the meeting. I'm still here for another 3-4 minutes.